So in this video, we're going to look at estimating the area under a curve using right endpoints instead of left endpoints. So we're going to take the same function, the same interval, and the same number of rectangles that we did in the previous video, except this time we're going to construct our rectangles using right endpoints instead of left endpoints. So the process is going to be mostly the same if you use right endpoints as if you than it is if you use left endpoints. So the first thing we want to do is recognize that if we're working over a closed interval from A to B, and we are going to construct n rectangles, that we need to know the width of each of the n rectangles. And so delta x, the width of the each of the n rectangles, is going to be given by b minus a. You do b minus a, the right endpoint of the interval, minus the left endpoint of the interval to get the length of the line segment you're working over. And then you divide that by n, the number of rectangles you're working with, and that will give you the width, delta x, of each rectangle that you're going to construct. So in our case, to get delta x, the width of each rectangle, we're going to take 2 minus 0. We're going to take the right endpoint of our interval minus the left endpoint of our interval. We're going to divide it by 4 because there are 4 rectangles. And so just like in the previous video, we're going to get that the width of each rectangle needs to be 1/2. The next step is to put tick marks in on your interval, tick marks that are spaced so that you use them to construct your rectangles. So the line interval from 0 to 2, if we rewrite it using a denominator of 2, because the width of our rectangles will have denominators of 2, starting at 0, we'll have 0 over 2, and our interval will go from 0 over 2 to 4 over 2, which is still 2. So the interval from 0 to 2 can be written as 0 over 2 to 4 over 2. And that's just using the denominator that establishes the width of each rectangle. And then you want to go in and put tick marks in. So I'm going to start at the beginning of my interval at 0 over 2 and put my first tick mark there. My second tick mark will go at 0 over 2 plus the width of the rectangle. 0 over 2 plus 1/2 is 1/2. So that's going to establish the first rectangle base with width 1/2. Then you take 1/2 and you add another half to it to get 2 halves. And again, like before, we don't want to reduce our fractions to lowest terms because we're going to be using sigma notation. So 2 halves plus 1/2 is 3 halves, and that'll give us a rectangle of width 1/2. And then we go 3 halves plus 1/2 to get out to 4 halves. And we're actually going to wind up with another rectangle here that's going to have a height of 0. This width is going to still be 1/2. So once you do that, you need to construct your rectangles, which I've pre-drawn, but you will, when you do your homework, need to draw them yourselves. And the idea is you want to identify, am I using right or left endpoints? And this says right endpoints, which means the upper right corner of each rectangle must be on the curve or on the graph of f of x. So what you do is you start at your interval. You say, I'm starting at 0 over 2. The next number over is going to be 1/2. You move over one number to the 1/2, and then you find the point, input 1/2, output f of 1/2. And that's going to give you the first right endpoint for your first rectangle. So when you construct a rectangle, drawing it over to 0 halves, which is the start of the interval, you're going to wind up with a rectangle whose upper right corner is on the curve. And that's what makes it a right endpoint instead of a left endpoint. From the 1/2, you go over to the next number. You input 2 halves into the function, so you get the point input 2 halves, output f of 2 halves, and it's going to give you the next rectangle where this point establishes the upper right hand corner of triangle number 2. You then step over from the 2 halves to the 3 halves. You find the ordered pair input 3 halves, output f of 3 halves. And then that establishes your next rectangle. And then you move over to the next point, the 4 halves, and you input the 4 halves, and you evaluate the function at 4 halves to get a point on the graph that establishes the upper right corner of your next rectangle. In this case, we get a rectangle that's a kind of a degenerate rectangle, because when we put 4 halves or 2 into our function, we see that we get a 0. We get a triangle, sorry, we get a rectangle whose height's 0, which is okay. So we want to notice that so like before, we're going to use these rectangles to estimate the area under the curve. I want to notice that each rectangle is a little bit under the curve. So in this case, my estimate's going to be an underestimate, and we could improve this estimate by increasing the number of rectangles. So if we make n larger, we get increasingly better estimates for the area under the curve. In this case, the estimate's pretty crude, but it is still an estimate. Estimates don't need to be perfect, otherwise we wouldn't call them estimates. So the area of each rectangle is going to be the height of the rectangle, which is going to be the output on this ordered pair. So this first rectangle, call it a sub 1. Its height is f of 1/2. So the area is going to be the height, f of 1/2, times the width. And the width or base of that rectangle is 1/2. This next rectangle, its height is going to be f of 2 halves. So the area of triangle 2 is f of 2 halves times the width, which is 1/2. And this third rectangle, the area of it, we'll call it a sub 3, will be the height of the rectangle, which is f of 3 halves. The function output gives you the height times the width, which is 1/2. And this third rectangle, a sub 4, its area is going to be f of 4 halves, which happens to be 0, which is okay, and then times 1/2 the width of that rectangle. So if we're approximating the area under the curve, the area under the curve, f of x, is going to be approximately equal to the sum of the areas of the approximating rectangles. So it's going to be just a sub 1, area 1, plus a sub 2, plus a sub 3, plus a sub 4. And those are equal to f evaluated at 1/2, which is the height of rectangle 1, times its width, plus the height of rectangle 2 times the width of it, plus the height of rectangle 3, that should be 3 halves, times 1/2, plus our last rectangle, its height is f of 4 halves times the width, which is 1/2. And as in the previous video, what we want to identify is that we can rewrite the sum using sigma notation. This is going to be the sum, and I want to notice the only thing changing is the numerator in the function inputs. It's starting at 1 and getting incremented by 1 until it gets to 4. So I'm going to take the sum from I equal 1 to 4 of the function evaluated at, and I'm going to rewrite the input as I over 2. So as our numbers increment from 1 to 4, we get 1 over 2, 2 over 2, 3 over 2, 4 over 2, times the width of each of the rectangles. And then once we have it here, this is something from a previous homework that we are able to solve using our summation formulas. And in the homework that goes with this set of videos, you're expected to use sigma notation and the summation formulas to find the estimated area under the curve. So I'm going to move to the next slide and just focus on the calculation that the area is approximated by this summation. So this is just grabbing that result from the previous slide and saying, okay, how do I use my summation formulas to simplify this result? So we know we were finding the area under the curve f of x equals negative x squared plus 4. So my next step would be to rewrite my summation from I equal 1 to 4. I look at this and I see that the 1/2 is a constant, so it can be factored out of the sum. And then this says everywhere in my function I see an x, replace the x with I over 2. So I'm going to come up to my function, and everywhere I see an x, I'm going to replace that x with I over 2. So this x squared becomes I over 2 quantity squared. And then we can start to simplify the summation. This is the sum, this 1/2, the sum from I equal 1 to 4 of the opposite of I squared over 2 squared is 4 plus 4. And if I wanted to, I could rewrite this 4 using a denominator of 4. So 4 could be replaced with 16 over 4. And the glory of doing that would be then I would have a common denominator of 4, which could be factored out. So 1/4 times 1/2 is an 1/8. And then I wouldn't have the denominators in that summation anymore. So I get 1/8, the sum from I equal 1 to 4 of negative I squared plus 16. It could be written, we could have written that as an individual step. I chose not to. So this equals 1/8. And now start to use those summation formulas. I'm going to break this into the sum of individual sums. I see that I have a negative I squared, so I'm going to factor the negative off of the summation. So the opposite of the sum from I equal 1 to 4 of I squared plus, and now I'm going to have the summation distributed into the 16. I get the sum from I equal 1 to 4 of the constant term 16. And now use summation formulas to simplify things. So I get the opposite from right here of the sum from I equal 1 to 4 of I squared. So the sum of the I squareds when n equals 4 we'll get by replacing each of the n's here with the 4. So I'm going to get 4 times 4 plus 1 is 5 times 2 times 4 plus 1 is 2 times 4 is 8 plus 1 is 9 all over 6 plus, and then I have the sum from I equal 1 to n of a constant equals the constant times n. So the constant here is 16 and n is equal to 4, so we just get 16 times 4. And some simplifying can happen with this ratio. We get 3 goes into 9 3 times and 3 goes into 6 2 times, and 2 goes into 2 once and 2 goes into 4 twice, so we can simplify that. So this equals 1/8 times negative 2 times 5 times 3 is negative 30 plus 16 times 4 is 40 plus 24 is 64. So we get negative 30 plus 64 is 34 over 8, and 2 will go into each of those evenly. So we get 34 divided by 2 is 17 over 8 divided by 2 is 4. So the area under our curve can be approximated by 17/4, and this is an underestimate for the area under that curve. And again, we could improve that estimate by increasing the number of rectangles we use to do our estimate.